Welcome to breadboarding. This is part 3 of video 12 of the breadboard video controller series for the Nanocomp 6809 breadboard computer. So this is the stage of the project where I've got a 640 by 480 two-color VGA graphics. I'm trying to get the classic Atari Lunar Lander game running. In parts 1 and parts 2 I covered the original games, and there's a Dublin Science Museum art exhibit that uses a JavaScript version of the game, which I've been basing some of the design for this project on. And in this part 3 what I'm going to do is show how I've actually got the basics of the game up and running, and some of the problems and challenges I've had in trying to do this. In particular, the main issue really being that the original Lunar Lander game made use of vector graphics hardware, so the CRT display actually took XY points to draw the lines, and joining up the lines was all part of the hardware, whereas because we're using standardized raster graphics, which are more common on more recent computers, we actually have to join up the dots ourselves. And even the JavaScript code that we'll be looking at makes use of JavaScript 2D canvas line drawing operations, which are able to, again, just draw vectors between points rather than having to worry about actually plotting the individual pixels between the points. So what I'm going to do first of all is just to remind you of the two versions of the Lander game we're trying to copy, and then I'm going to take you into the code and give you a quick overview of the code before showing you the running Lander game. So I'm just going to take a look at the JavaScript Lander game. This came from an art exhibit at the Dublin Science Museum, and it's still available at the URL up here. If you look at part 1 and part 2 videos, I include all the links for these in the descriptions. So this is the JavaScript code that we'll be basing this on, and you'll see that the landscape should be fairly familiar, and we're using some of the point plotting information from this Lander game to base our Nanocomp 6809 version written in C. And if we also then have a look at MAME, the original program running under MAME, which again we covered how to do this in the part 1 video. So you just have to press the 5 key to put some coins in, press 1, and this one uses slightly different keys. We use the control key for thrust, but you can see here it looks again pretty similar. But the design of the landers, I've actually copied screen captures of the landers in this particular version of the game, the original game, and when we come in close to when the altitude reduces below a certain amount, you'll see that it will go into a zoom mode and the lander becomes a lot more detailed then. So we've based the landers that I'm using in the Nanocomp code to be very much based on this version rather than the JavaScript version of the game. Which will probably crash. So that's enough of the current versions. What I'm going to do now is to take you into Visual Studio Code and I'll have a quick look through the code from the original JavaScript version of the game, and this will help to set this within the context of the code that I'm going to be showing you in C. So these are the files which are downloaded from the website here. So the game.js is the main part of the program. There is then Lander.js, which is the Lunar Lander object itself, and this has data and methods which are used to manipulate the lander. So for example, render, update, moves it down the screen based on gravity and the other things. Also then the render shapes actually draws the lander using vector line commands. And then the landscape data, which is where the landscape information is used, and the zone information, which shows where the multipliers are shown for the different landing zones. So this code here has been used as a basis for it. I probably could have had my own design of this and gone back and perhaps done it from scratch, but I felt that this would probably allow me to get up and running more quickly, and has caused some complications because of some of the ways how the zoom functionality is done in JavaScript code makes use of some of the transformation and scaling operations which are available under JavaScript 2D canvas context, which took me a little while to get to the bottom of, to work out how to do things. But fundamentally the game is the main part of the program that does everything, and there is a loop function or method in here, and this basically controls the main part of the game. And what we're doing really here is maintaining some sort of counter or time. So I've just used counter because we don't really have a clock on the Nanocomp at the moment. And there is some logic in here to do with how many frames per second the JavaScript code is updating. Well, the Nanocomp can't do anywhere near as fast as this, so we're only looking at probably 4 or 5 updates to the screen per second at most. So we really don't have to worry about 60 frames per second and how we're doing things. And there are various calls here to call the Lander update routine. Looking at the game state, so for example, there are a number of game states that will come across when we're doing this. Playing is the main one when it's actually working, but then there are also things like crashed and landed and also waiting. So the screen that you see at the beginning of the game where you're waiting for the player to start is also on. We've also got then here the render code. So in particular, the render code does a couple of things which it took me a while to get to the bottom of. These context information, which is the 2D drawing context which is used to draw the screen. The couple of key things it does: every frame it clears the whole screen and then it draws the picture fresh each time. And what it also does is use the view object X and Y coordinates to transform the root or the base origin of the 0, 0 for where the top of the left of the screen is, and also that's adjusted by the scale as well. Now these two things are quite important when we look at the zoomed view when you get the large lander, and it took me quite a while to work out how to transform and translate these into the C code. And then we can see here the landscape render and lander render basically then draw those. Now in the C code, because I'm not going to be clearing the screen every single time and then redrawing the entire picture, what I'm going to do is the landscape will just be rendered when it's needed, and will then just move the lander around the screen. So it's slightly more complicated way of doing things because we're only moving the bits that we need to move, whereas this JavaScript code basically just cleared the whole screen and just redraw it from scratch every single time, which, because the processor here is running probably 1,000 to 10,000 times faster than the 6809 and Nanocomp, then we can get away with doing that. But unfortunately, this won't work with our 8-bit processor. So I'm not going to go through all of the stuff here because we're largely going to cover this when we get into the C code. But within the landscape data, there is the vectors or the array really of the X and Y values of where the landscape is actually drawn, and that's quite useful, and we'll be using that. And then also where the flat areas are, where the landing zone is, we've also got the multipliers for when we see the 5 times, 4 times, 2 times flashing areas, then that comes from this information. But it isn't quite as simple as that, in that there's about 11 landing zones, 0 to 10, but there are different combinations. So depending on the cycle at which it goes through, the zones which are flashing will vary from cycle to cycle. So when you go from one page to the next page, you'll get a different set of landing zones. So all that sort of code has been reproduced in the C here, but it took quite a while to work out what was going on here. So that's what we're basing this on, and obviously JavaScript is object orientated, whereas the C code that I'm doing isn't object orientated. But what I've tried to do is to maintain some level of similarity in the naming convention on how this is done. So let's close this down now, and I'll go into the C code and just explain some of the challenges and things I've had, and then we'll go in to run the program. So this is the C code. So I've tried to retain the naming of the files very similar to the JavaScript game, although now obviously we've got C and .h on the end there. And what I'm just going to do is explain the high level working of the game, and then we'll go in and actually show it working. The main game is in itself turned in Lander game. So Lander game is where the thing actually gets started from, and the main function down the bottom, which is what starts, we change the standard output for all of the C print functions to actually the serial port. So this is how we can do the serial port debugging. We're initializing the graphics, which is some C code that I covered in the last part 2 where we're initializing the graphics mode and making sure that's all set up properly. We then create a Lander game object. So what I've done here is, rather than passing lots of variables between all of the functions and procedures, what I've done is created a couple of sort of global variables. So the Lander game variable and the Lander variables are the main two variables that we're working with. And basically that means then that we can access the variables anywhere within the code without having to pass these particular things around the place. Setting the game over and initializing the landscape. This initializes some internal information needed for this, and then the loop basically does the main processing until such time as the exit game key is pressed. I think I've used the CN cancel or continue key from the Nanocomp, but it's a CN for cancel I've used it as. So if you press that, it'll actually exit. And so really the loop does most of the work here. So if you drill down into that, and you'll see here that we've got the various game states, and the game states, waiting is when we have the demo screen just going over and over again, waiting to play. Then we have playing. Then there will be other states such as game over, crashed and landed, which will also affect the way how things work. What this loop does is at game over status, we clear the screen, we draw the main high-level landscape, we force the text labels at the top of the screen to be drawn, and then restart level basically restarts all of the variables and things necessary to restart a game. Then generally when we are waiting or when we're playing, then we're checking the keys, so whether or not we've pressed any of the left, right, the thrust keys, for example. And then once we've determined the keys, we'll then update the lander. So this will update the various variables and things for the lander, its position, its current velocity, and the rotation, and then how the thrust actually changes the velocity in the two axes. What this will also do is, when it's running in the waiting mode, then basically when the altitude gets below a certain level, then it will just restart it. So that bit of the loop just basically makes the front screen loop. And then whilst it's playing, it'll also run a routine that checks collisions, and basically if the collision is detected, then it will update the game state to crashed. Now, the bit that's probably the most complicated I came across with this update view, and this is all to do with updating the transform information used for displaying the large lander view, the zoomed lander view, and then the render, in fact, is quite straightforward. In fact, what this actually does is just calls the lander render, and then our counter, so the time that we're looking at within this particular code is just the counter. So effectively it's the number of loops that it's done, and it's currently running at about 4 or 5 loops per second, which isn't particularly smooth, but it's good enough to give a reasonable playable game. So the main challenges I had in doing this particularly is more to do with the zoom level, and I'll explain about that once we've actually shown you how this works. Within here, the other key classes that we've got, or the other key files here, are not really classes, our landscape. Now what I found when I was doing this, there were a couple of X values here where there were fractional points. So for example here we might have had a 19.6 and a 19.6 here, or a 19.7. So what I have had to do is to look at the duplicates here, and in a few of the areas I actually needed to change the values just so that they were the next value, because it caused some problems when doing some of the calculations, particularly for collision detection. So the base data that came out of the JavaScript code, because it was using floating point, that didn't matter so much, but because I'm only using integer arithmetic here, I needed to massage some of the values here so that where I had 2 values which were the same, I needed to make them at least 1 pixel difference. So this data that we've got for our landscape here is very similar to the original game and the JavaScript version of it, but there have been some slight modifications a few places. The available zones again is based very much on the data that was defined in the JavaScript code, and again the zone combinations has been done there. And then we've actually got the code that does some initialization. There's a particular array that I maintain that allows me to look up for a given x coordinate what is the point to the left hand side that actually matches that coordinate. That's quite important for when we're doing lookups and things, rather than doing a big loop that the JavaScript code just went in a big loop going through all the points to see which one matched, where that was really too slow. This is a lot faster for the C code under the 6809 to pre-calculate that. So, and you'll see a number of places where we've got printfs. This will currently output debug information to the serial port. At the moment, there's probably a bit too much debug information enabled at the moment. I'll probably turn some of it off a bit later, but it's interesting just to see the sort of information that you get out. And this in particular was allowing me to look at this X to point array to make sure that I was actually getting the right information coming out, particularly when doing the collision detection. It was quite complex. And there's also a routine here I did have for drawing a scale on the screen to make sure when I was debugging to see whether or not anything was lining up properly. We've got the Zoom version of the landscape drawing code, and this basically draws all the points, and then it goes through and also then draws the ×2 ×5 multiplier for the given landing zones if necessary. And then we've got a similar thing for the main landscape is very similar. Some of the calculations are a little bit simpler. In the zoomed version, we actually have to do some calculations to deal with the zoomed level. So in fact, the zoomed view has got is at 4 times magnification effectively. Okay, so that's the landscape. The lander is probably the other big one that we need to look at, and the header file for the lander defines a number of types. So we have here the game state, so you can see is waiting, playing, landed, crashed, and game over. So those are the states of the game. We then have the game view. So this was based on the transformation that was needed for the JavaScript 2D work, and the X and Y value and the scale were used for doing the transformation for the JavaScript canvas. So it made the JavaScript zoom much easier to do on in JavaScript than it was to do on the Nanocomp here. And then we've got two structures, one for the game itself, which has all the things like the gravity factors, thrust acceleration, what the top speed and drag and things like that are. And then we've got the variables which are used to track the lander itself. I won't go through all these, but it's mainly the things like altitude, its XY position, velocity, rotation, and the previous old versions of these. So when we're erasing the old lander and then drawing the new one, we know where it was before and where it is now. So the lander has the render functions here, which are basically just calling the raster move functions that I had last time. So these were in the previous video. This sort of large lander and small lander raster move would move the raster image of a particular lander in a different each orientation, one position on the screen to the other. So that's almost the same, although I had to simplify these somewhat because the code was getting too big to run within the 32K of RAM that I've got. And so in fact the large lander raster move in fact now actually calls this move large block 3 times. So rather than having this code duplicated that I had in, effectively in line, I've actually now moved this code out into a common function here, which is called 6 times. So this has actually reduced the volume of the code quite a bit, and it's meant that I can squash things in a bit. So it's basically the same code that was running in part 2, but it's been optimized a little bit for size because it was getting far too large and I wasn't able to fit everything in the memory. And then this is the move small block, basically is very similar to the code that we had last time. So the main areas of the lander itself is the rendering of it, and there are some calculations in the code here. So the update function includes all the various things to do with moving it around, calculating fuel, what's happening with the thrust, setting the old position from the current position, working out velocity, so including some drag. So basically the X velocity reduces over a period of time according to a drag factor. And the other key thing I've had to do here is, because I'm only using integer arithmetic, whenever there's any need for using fractions, what I've been doing is effectively working with the bottom 3 digits as being the fractional part, and then either multiplying or dividing things by 1,000 to scale that. So in particular, when I was trying to get things to work and you having gravity values which worked out at less than 1 pixel per turn, if I didn't actually calculate things at a higher degree of precision, things would never move down the screen because gravity might only be 0.1 of a pixel per turn that it would actually affect. And so you might find that over a period of time, the rounding of these things results in no movement at all. So there is some logic in here to avoid having to use any floating point, in that there's no floating point available on the Nanocomp C environment, just because the CMOC C compiler will only work with floating point if you have a basic floating point ROM installed on the computer. So we don't have that. So the actual movement of the lander is very much done in this code here, and we do have different information around the lander to do with which scale it is, so whether it is used in the large scale or if it's in the small scale. So there are different values that we need to worry about that. So that's based, and then there's a few things to do with the crashing. At the moment, there's nothing specifically to do with crashing and exploding. At the moment, you just get the message. I haven't implemented any crash logic. So there are some areas where I've made simplifications for the moment, but I just wanted to get the lander game working with a video card so I could get on and do the next stage of the hardware. So the programming of the lander has tended to be a lot more complicated than anticipated, and I really don't want to make this mainly a programming project. I want to do more about the video hardware. So I'm going to show you now the lander game as it is now. Hopefully what I'll do is I might look at optimizing this over the next number of weeks and things, that when I do the next round of the video card consolidation, I'll see if I can get both the Tetris game and the lander game running on the modified video controller. So this is the latest compile command that I've got for this. So we're starting it at 000, the origin, where I've had to keep on modifying where the data is, and this limit here is also important because if we go too high, we start interfering with the Nanocomp stack and the user stack, and so what you get is strange things occur halfway through the program where it starts to overwrite its stack. So there are some useful things in here that will check to see if any of the code's going to start writing over the stack space, and our int dir here means that it expands all of the intermediate assembly language files and things, which is quite useful for helping with troubleshooting and looking at the specifics of the code. So we've got here the lander game, the Nanocomp common library that I had from the Tetris game, the lander class itself, and the landscape. So those are basically the components that we need. There's a few warnings about some of the constant declaration character arrays being passed into a draw message function, but that's basically the code. And if we just look at the SREC, we look at it actually with more attributes. So you can see here that in fact the SREC file it's produced is now about 81k. So it's getting quite big. This means it's getting up to about 30k in actual code. And so I have had to adjust some of the debug statements and modify the code over time to make sure that I keep within the memory constraints. One of the things that's most useful, as I said, about the internal int directory here. So the lander game map, for some of the internal files which are created, this is part of the assembly language and linking. But what this actually shows in the map file is where all the various modules and things are loaded. But what it does show is that we're starting to load the data at 7400. And it also shows the highest amount of data being used here. So what we have to do is to make sure that this number here doesn't overwrite the stack, because if this does overwrite the stack, then we're in trouble. So some of these intermediate files that get produced here are actually quite useful. We could also look at for example, the landergame.list there. Landergame.list here shows the intermediate assembly language which is generated by the code, and it's also interesting to see that where the arrays are defined here, because we define the arrays as global constants, rather than having commands like load B with an immediate value, then store that value in the array, these arrays are actually defined in using the FCB sort of declaration in the assembly language. So it means that arrays defined in this way are much more memory efficient. They don't take as much memory as they would as if they were done privately within the individual functions themselves. So making use of global arrays like this has managed to manage the memory a lot better. Okay, so what I'm going to do now is to just reset the Nanocomp first. What I'm going to do now is to go to the screen share, the VGA capture. So you'll see this is running, this is just the blank screen. All I'm going to do now is to go into the Nanocomp, hit load, and we're going to send the Lander game SREC file. So you remember in the previous video, I've speeded up the serial comms from 9600 baud up to about 57k. So it runs a lot faster than it did previously, but now because we're up to about 80k of SREC file, then it still takes 20 seconds or so to download. So I might look at speeding that up at some point in time. Right, so that has finished. Now I'm going to run this up the first time. Now to start with, this will be using the VGA screen fonts that exist in the basic video card by default. So these fonts have not been customized to work with the Lander game. But if I just run this up, you can sort of see that as we clear the screen, there's quite a lot of debug information being output, and that does slow things down quite a bit because of the serial comms. It's actually outputting quite a lot of data. And you'll see here that now we've got the sort of the waiting mode, the waiting screen here. So you can see the Lander going across. There is some snow here. The snow, as I've said in the previous part 2, is because we're not coordinating the video RAM access and updating from the CPU at the moment. And what I want to do is to get onto the hardware and update the CPU to make it faster, and also avoid all this snow in some later videos. So you'll see there it then goes down into the zoomed view just for a few frames there, and then goes back to again. So what you'll see here though is that the fonts which you've got up here, these are standard VGA fonts. They don't really look very much like the ones which are used in the Lander game. So what I have done, if I switch back to DOSBox here, so what you can see here is the fonts here. The default font are quite wide, so there's 2 bits for each of the characters, and if we go to look at the other characters, you can see that they're quite wide. Now in fact in the Lander game what I did is I went through and created or modified these to be much thinner fonts which match the way how the Lander game works. So you can see here I've gone through for certainly the numbers and some of the figures. And what I also did is we needed some arrows for the up, down, left, right. So I did some arrows, and I modified the greater than and less than signs here to actually be used as the arrows for the display as well. So this Lander 2 F16, this is a sort of customized VGA font that has got the Lander sort of style, sort of single pixel width characters, which looks much closer to the vector graphics. And what in fact I did there was I converted that into an S record format. So in fact here what we can see is where I switch back to, I can send the Lander font SREC. So what I'm going to do now is to load that, and then when we switch back to our VGA capture card, so you can see here that the fonts here are quite big and thick. And now if I just start this again, so this is the Lander game using the modified Lander VGA font. So this font is much closer to the vector drawn characters of the original game that we saw on MAME. You can see also on the right hand side there the left and right arrows and up and down arrows that we designed to match the original Lander game. Now this will, when it gets below a certain altitude, will go into the zoom mode, which is about 4 times the resolution. Then it will switch back up to the top there. Now what I have done here is added a key F, which will add extra fuel or credit. And so what I'm going to do in a minute is we will start the game and see if we can land in the 2 time zone. So I'm going to press S to start the game. We'll just press F a few times to add some fuel, and then we use the 1 and the 3 keys to rotate and the 2 key for thrust. Now at the moment we've not got any flames for the thrust. That does make it a little bit more difficult to keep an eye on what's going on. But what I'm going to try and do first of all is to get over the zone where we want to land with the horizontal velocity. So we've just gone a little bit too far over there. Key thing is here is not to get too fast going down, because it becomes quite difficult to slow down. The horizontal speed will have some level of drag, so it will tail off over a little time. So now hopefully we should just be able to drift down onto the landing pad. And if we land below about 500 at the moment, then that should be good enough for a good landing. At the moment the speeds are multiplied by 1,000, and I need to scale them to be closer to the original Lunar Lander speeds, which were somewhere around about 120, I think, with the maximum speed. So now when we get down into the zoom, we just need to make sure that we try and carefully hit the thrust so we don't overdo it. It's very easy to overdo the thrust and you start going back up again. So I need to modify the sensitivity of the thrust and how long it takes to die off. So if we can get this to below about 500, then we should have quite a soft landing. Congratulations, a perfect landing, 50 points. Excellent. So I hope what I've shown here, I've managed to get the Lander game working to some level. It does need some level of optimization, but I didn't want this project mainly to be about programming. I wanted to really focus on the VGA hardware. So what I'm going to do is to start to build out the 256 color graphics, which is slightly lower resolution. It's 320 by 200, but 256 colors out of a palette of 262,000. And this should mean that it will be able to show images very close to a lot of the original DOS VGA games, which tended to use that mode. In the next video, what I'm going to be doing is upgrading the VGA controller to be able to do that 256 colors at that slightly lower resolution, but we'll have 8 bits per pixel to do the color. What I will do is come back to the Lander game probably in another month or two, once I've managed to get the video controller to do both character-based high-res 2-color graphics and medium-res 256-color graphics. What I'll do is get both the Tetris and the Lander games working on that, and I'll try and optimize them in the meantime and get them working a little bit more smoothly. But it's got to the level where I wanted to with this, and hopefully you found it interesting and useful. So if you don't want to miss out on any future videos, please hit subscribe, and if you found it interesting, please hit like. It does help to make the videos available to a wider number of people. Thanks for watching.